Welcome to the Master Electrician Prep Podcast, your go-to source for mastering the kind, sharpening your skills, and passing the exam with confidence. Whether you're driving to the job site or studying late at night, we're here to break down the NEC, tackle real exam questions, and give you the tips and strategies you need to become a licensed master electrician. Let's get wired in and power up your future. The journey starts now. Please like and subscribe again. Today we're doing a deep dive into conductor ampacity and protective devices. And really, this isn't just another chapter. It's fundamental.
Absolutely. It's really the core of electrical safety, system reliability, foundational stuff if you want to master the NEC and, ace that exam.
So what's our mission today?
Well, we want to pull out the really essential nuggets from the study materials. We're going to break down how conductors carry current safely and, maybe even more importantly, how we protect them.
Protect the conductors and the whole system, right?
Exactly. From harm, from overloads, shorts, all of it. Understanding this isn't just about a test score. It's about making sure every single installation is safe, truly robust.
Okay. And we're working directly from a key chapter in an exam prep guide. So the goal is cut through the dense language, get clear understanding.
Highlight the real-world stuff.
Yeah, practical applications, and really arm you, the listener, with what you need for those tricky scenarios, job site or exam room. Let's get into it. So, starting right at the beginning, every circuit needs conductors. That's how the path gets completed.
Basic but crucial.
And those conductors rely on insulation. Kind of the unsung hero, right? Keeps the current in line, prevents shorts, ground faults.
Definitely. And, a conductor's lifespan, it really depends on a few things.
Like what?
Well, its insulation type is big. Also, the operating conditions hot, wet, dry, and, of course, how much load it's carrying constantly.
Makes sense.
So the bottom line is these conductors absolutely must be protected against overloading, against short circuits, against ground faults. That's the job of OCPD's overcurrent protection devices. They're the safety net.
Got it. And as we go through this, we have some specific targets, things we want to nail down. Like what actually counts as a current carrying conductor? How do we usually figure out ampacity? How does ambient temp affect conductor size? That's a big one. We'll also look at the neutral conductor, sometimes confusing, dim rating and crowded gutters, ampacity of bus bars.
Yeah, even bus bars.
And finally, introduce the three main types of OCPDs. Sound good?
Sounds like a plan. Let's dive in.
Okay, Article 310. This is conductors for general wiring. It sets the stage, covers requirements for conductors pretty much everywhere. Dwellings, offices, industrial sites, rated up to 2,000 volts.
And it gets specific on materials too, right?
Yeah.
Copper, aluminum, or that copper-clad aluminum.
Exactly. The code lays it out.
Now, the physical characteristics are pretty interesting here. Sizes are AWG American wire gauge for smaller ones and case mills for the bigger conductors.
Right.
And here's a rule that sometimes trips people up. Conductors 1 AWG and larger, they have to be stranded if you're putting them in a raceway.
Must be stranded. Why is that?
Flexibility mostly. Easier to pull, less likely to get damage going around bends. But then conversely, conductors smaller than 8 AWG cannot be stranded if they're in a raceway.
Okay, smaller than 8 AWG cannot be stranded in a raceway.
Right. Different reasons there, mostly about secure termination. So these physical rules aren't arbitrary. They tie into reliability and installation practice.
That makes sense. And you mentioned types of conductors earlier. The NEC breaks them down by their covering.
It does. You've got bare conductors, like some grounding conductors, no covering at all.
Okay.
Then covered conductors. You have a material covering, but it's not rated as NEC insulation, maybe just for physical protection or specific uses.
And then the standard?
Insulated conductors. These have a covering that the NEC specifically recognizes as insulation, providing that electrical protection.
Got it. Bare, covered, insulated. Now, what about current carrying conductors? Seems obvious, but...
Yeah, it seems simple, but the definition matters for calculations.
Yeah.
Basically, any ungrounded conductor carrying current is considered current carrying.
Okay. Ungrounded conductors carrying current.
But, and this is important, there are exceptions. Sometimes the neutral conductor isn't considered current carrying.
Oh, when is that?
Specific cases, like certain fire alarm circuits mentioned in the code. Knowing these exceptions is key, so you don't over-durate or oversize things unnecessarily.
Okay, good to know. So we've covered individual conductors. What if one wire isn't enough for the current?
Parallel conductor.
Exactly. You take two or more conductors, connect them electrically at both ends, and they act like one single beefier conductor.
But there are strict rules for doing this.
Oh, absolutely. Section 310.1G in the NEC is critical here. If you ignore these requirements, you're asking for trouble.
What kind of trouble?
Unbalanced current flow. For them to share the load equally, they must have the exact same length.
Okay, same length.
Same conductor material, all copper or all aluminum.
Same material.
Same size, like both 40 or whatever.
Same size.
Same insulation type.
Same insulation.
And this is key too, terminated in the exact same manner. Wow, okay. Everything has to match perfectly.
Precisely. Any difference, and one conductor might carry more current than the others, overheat. While the others aren't pulling their weight, it compromises the whole setup.
That makes sense. Safety and lifespan depend on that balance. What about the grounding conductors when you parallel?
Good question. For equipment grounding conductors run in parallel, they can actually be smaller than 10 AWG. You size them based on table 250.122 in the code.
Okay, separate rule for those. Now back to conductor sizes generally. The NEC lists a whole range.
It does. Copper, aluminum, copper-clad aluminum. Starts tiny at 18 AWG, goes all the way up to 2,000 kilocimo. Massive range.
But for most general wiring, like in buildings up to 2,000 volts, what's the minimum?
The floor basically is 14 AWG for copper and 12 AWG for aluminum or copper-clad aluminum. That's your starting point for branch circuits and the like.
Good baseline to remember. 14 copper, 12 aluminum. Okay, let's talk insulation again. Section 310.0 has the details.
Yeah, this section is packed with info on insulated conductors where you can use them.
Yeah.
And this is where it gets interesting because the insulation type and the conditions.
Wet, dry, damp.
Exactly. They directly determine the conductor's ampacity.
Yeah.
Especially its maximum operating temperature. Think of it like its thermal speed limit.
Thermal speed limit, I like that. And some insulations can handle higher temps.
Right. The code recognizes types like, say, RHW2 or XHHW2, which are rated for higher temperatures, even in wet locations. Choosing the right one for the environment is crucial.
So what exactly counts as a wet location, according to the code?
Article 100 defines it. We're talking about conductors buried directly in the earth, inside a concrete slab on or below grade, maybe installed on a rooftop exposed to weather, or in areas subject to like regular washdowns, like in some industrial or food processing areas. You have to identify these up front.
Right, so you pick the right conductor. How about identifying conductors? Color coding and marking.
Yep, section 310.6 covers that. For grounding conductors, 6 AWG and smaller, it's pretty standard. Green or green with one or more yellow stripes.
Okay, green for ground. Larger ones.
Larger grounding conductors and ungrounded or neutral conductors usually rely on marking at the terminals or other means of identification, sometimes color tape.
And for multi-wire branch circuits.
Yes. Section 210.5C requires that the ungrounded conductors in multi-wire branch circuits connected to different phases or systems be identified, usually by color coding or other durable means. Super important for safety, especially during maintenance. Helps avoid mixing up phases.
Absolutely. Okay, let's get to the heart of it. Ampacity. What is it exactly?
Simply put, ampacity is the maximum current in amperes that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating.
Continuously, without exceeding its temperature rating, so ignore it.
And you risk overheating. Insulation breaks down, connections degrade, and you could easily start a fire. It's fundamental to preventing damage and ensuring safety.
And lots of things affect that actual ampacity, right? Not just the wire size.
Tons of things. The insulation type we just talked about, the operating conditions, wet, dry, ambient temp.
Yeah.
How many other current carrying conductors are bundled with it?
Right, conduit fill.
Exactly. The type of raceway or cable it's in, and definitely the ambient temperature around it. Section 310.14 lays out the methods for figuring out the allowable ampacity, considering all these factors.
This is where those tables in the code book or your study guide become essential. The conductor insulation tables.
Your best friend, absolutely. They list allowable ampacities based on those key temperature ratings, 60 degrees C, 75 degrees C, and 90 degrees C. You have to know which column applies to your conductor type and situation.
And that leads to the allowable conductor ampacity, where you might have to adjust or derate based on conditions.
Precisely. You start with the table value, but then you have to apply correction factors. So if someone asks, what's the ampacity of a 1 AWG THW copper conductor?
You go to the table, find THW copper, look in the correct temperature column, likely 75 degrees C for THW.
Right. Same process for, say, a 20 AWG THW aluminum conductor or a 4 AWG XHW conductor in a conduit. You find the base ampacity from the table, then consider if any derating is needed for temperature or conduit fill.
Let's talk about that ambient temperature derating. It seems really significant.
It is. A conductor gets rid of heat into the surrounding air. If that air is already hot, the conductor can't cool itself as effectively, right?
Makes sense. So its current carrying capacity goes down.
Exactly. The NEC provides correction factor tables based on ambient temperature. You find the expected ambient temp, find the factor, and multiply it by the table ampacity.
Can you give an example?
Sure. Let's say you have a 30 AWG THW copper conductor. Table 310.16 might list its ampacity at, let's say, 200 amps in the 75 degrees C column, but it's installed in a location where the ambient temperature is 50 degrees C, which is pretty hot.
Okay, 50 degrees C ambient.
You look up the correction factor for 50 degrees C for a 75 degrees C rated conductor. Let's say that factor is 0.82. You take the 200 amps, multiply by 0.82.
200 times 0.82 is 164 amps.
Right. So its allowable ampacity in that hot environment is only 164 amps, not 200. Big difference.
Wow, yeah. Another example, maybe with bundling.
Okay, how about a 2 AWG THW aluminum conductor? Maybe its base ampacity is 100 amps, but you have, say, 12 current carrying conductors crammed into one conduit.
12 conductors? That's a lot of heat.
It is. You look up the adjustment factor for having 1020 current carrying conductors in a raceway, which is 50%, or 0.50. So 100 amps times 0.50.
Only 50 amps.
See, conduit fill derating can be massive. These adjustments are absolutely critical for safety.
And you mentioned rooftops earlier. Sunlight makes it even worse.
Oh, yeah. Raceways exposed to direct sunlight on or above rooftops get extra hot. The code even tells you to add temperature adders based on how close the raceway is to the roof surface. If it's right on the roof, say less than 78-inch space, you might have to add 60 degrees F or 33 degrees C to the ambient temperature before you even apply the correction factor. That rooftop heat is no joke.
Definitely something to watch for. So, we covered temperature and conduit fill derating. Now, that tricky neutral conductor, when is it considered current carrying for derating purposes?
Okay, section 310.15E is where you look. The general rule is a neutral carrying only the unbalanced current from other conductors in the same circuit isn't counted. Unless it's part of a 3-wire circuit from a 4-wire 3-phase Y system.
Okay.
Or, and this is the big one, if it's a 4-wire 3-phase Y circuit supplying predominantly non-linear loads.
Non-linear loads, like what?
Think computers, electronic ballasts for fluorescent or LED lights, variable frequency drives for motors.
Yeah.
These loads draw current in pulses, not smooth sine waves.
And that affects the neutral.
Massively. The harmonic currents generated by these loads don't cancel out on the neutral like balanced linear loads do. In fact, they can add up on the neutral. So the neutral can end up carrying significant current, sometimes even more than the phase conductors.
Wow. So in those cases, the neutral must be counted as a current carrying conductor for derating.
Absolutely.
Yeah.
You have to account for that extra heat it's generating. Ignoring it is a common and dangerous mistake with modern loads.
Good to know. Okay, let's shift slightly. Specific rules for residential services and feeders. Section 310.12.
Right. The code has some specific allowances here, particularly for dwelling units. There's a common practice, often permitted by 310.412, allowing you to size the service or feeder conductors at 83% of the service rating.
83%. How does that work in practice?
Or take a standard 200 amp residential service. You take 200 amps, multiply by 0.83, that gives you 166 amps.
Okay, 166 amps is the minimum calculated load.
Right, so you then select the conductor from the 75 degree C column of table 310.16 that has an ampacity of at least 166 amps. A 20 AWG copper THWN or THHN is rated 175 amps at 75 degrees C. So that often works perfectly.
So it allows for slightly smaller conductors than you might otherwise calculate for a 200A load.
Generally, yes, for those specific dwelling unit applications up to 400 amps. Over 400 amps, the standard calculation methods usually apply again.
Got it. Now here's something you mentioned that sounds critical. Terminal temperature rating.
Hugely critical, often overlooked. Here's the deal. A conductor might have a high temperature rating itself, like 90 degrees C THHN, but its ampacity in practice is limited by the lowest temperature rating of any terminal, device, or conductor connected to it.
So the connection point can be the weak link.
Exactly. Most standard circuit breakers and equipment terminals, especially for circuits 100 amps or less, or using conductors 1 AWG or smaller, are only rated for 60 degrees C or maybe 75 degrees C.
So even if I use 90 degrees C wire?
You can't use its 90 degrees C ampacity value if the breaker terminal it lands on is only rated for, say, 75 degrees C. You have to use the ampacity from the 75 C column of the table for sizing that circuit.
Okay, so you check the wire rating, check the terminal rating, and use the lower of the two readings to determine the allowable ampacity from the table.
That's the rule, section 110.14C. For circuits over 100 amps or using conductors larger than 1 AWG, you might find 75 C terminals are more common. But you still have to check and use the appropriate ampacity column. Ignoring terminal ratings leads to overheated connections, insulation damage right at the termination, potential failures.
Definitely a key detail. Okay, sizing conductors for branch circuits now. Basic idea. Size for the load, protect with an OCPD.
That's the core principle. And a huge part of sizing for the load is accounting for continuous loads.
Right, the 125% rule. What's a continuous load again?
Any load expected to operate for 3 hours or more continuously. Think lighting in an office, certain heating equipment, maybe some machinery.
Okay, 3 hours or more. And the rule.
For continuous loads, the branch circuit conductors need to have an allowable ampacity of not less than 125% of the continuous load, plus 100% of any non-continuous load on the same circuit. The overcurrent device is also sized similarly, 125% of continuous plus 100% of non-continuous. That's in 210.1 Mon A for conductors and 210.20 A for OCPDs.
Let's break that down with an example. Say I have a 2 AWG THN copper conductor. Table says 130 amps at 75 degrees C, assuming 75 degrees C terminals.
Okay, 130 amp wire.
But it's feeding a continuous load. Can I load it right up to 130 amps?
No. Because of the 125% rule, the maximum continuous load you can put on that 130 amp rated conductor is actually 130 amps divided by 1.25.
130 divided by 1.25 is 104 amps.
Correct. Or think of it the other way. 130 amps times 80%, which is the inverse of 125%, is 104 amps. So that 130 amp wire can only handle 104 amp continuous load safely according to the code. That 25% headroom is built in for heat dissipation under continuous operation.
That's a really important calculation. 125% of the load for sizing or 80% of the wire breaker rating for maximum continuous load.
Exactly. Got to get that right.
Okay, moving beyond wires for a sec. Bus bars. What are they and how do we figure out their ampacity?
Right, bus bars. You see them in switchgear, panel boards, motor control centers. They're usually solid rectangular bars of copper or aluminum, big current carriers.
How do you calculate their ampacity? It's not in table 310.16.
No, it's different. It's often based on the cross-sectional area. A common rule of thumb, though manufacturer's data is best, is around 700 amps per square inch for aluminum, and maybe 1,000 amps per square inch for copper in free air.
So amps per square inch. Example.
Sure. So you have a copper bus bar that's 4 inches wide and half an inch thick.
Okay, 4 by 0.5 inches.
Cross-sectional area is 4 times 0.5, which is 2 square inches. If we use the 1,000 amps per square inch rule, that bus bar could potentially handle 2 times in 1,000 or 2,000 amps.
Wow. Big capacity.
Yeah, they're designed for heavy lifting, electrically speaking. Conditions like enclosure and cooling matter too, but that gives you the basic idea.
And quickly, medium voltage? Conductors over 2,000 volts.
That's covered in Article 311. Different set of rules, different tables, specialized stuff for higher voltages. We won't dive deep there today, but no, it's a separate article.
Okay, good overview of conductors and ampacity. Now let's talk protection, overcurrent protection devices. OCPDs.
The guardians of the circuit, as you said. Absolutely vital. Their job is to interrupt the current flow before the conductors overheat due to overloads, or before serious damage occurs from short circuits or ground faults. Section 240.4 lays out the general requirements.
And the main types we encounter?
Primarily 3. Plug fuses, cartridge fuses, and circuit breakers.
Fuses and breakers.
Right. And remember the sequence. Determine the conductor's allowable ampacity first, considering all D rating factors. Then select the appropriate OCPD based on that ampacity and the load.
Okay, conductor first, then protection. How do we size the OCPD generally for circuits 800 amps or less?
Generally, the conductor needs to be protected by an OCPD set at a rating not higher than the conductor's allowable ampacity, after all adjustments.
Okay, protection shouldn't exceed ampacity.
Right. But there's a common exception, the next size up rule in 240.4b. If the conductor's ampacity doesn't correspond to a standard OCPD size listed in Table 240.6, you're generally permitted to use the next higher standard size OCPD, provided the conductor ampacity isn't exceeded by too much, specific conditions apply, the OCPD rating is 800 amps or less, and it's not supplying certain types of loads like multi-outlet receptacle circuits where the rules are stricter.
The next size up rule, that's important. What about over 800 amps?
Over 800 amps, that next size up rule generally doesn't apply. If the conductor's ampacity doesn't match a standard fuse or breaker size, you typically have to use an OCPD rated at or below the conductor's ampacity. Or size the conductor up so its ampacity matches or exceeds the standard OCPD rating you need to use. It's stricter for those larger circuits.
Got it. More stringent over 800A. What about small conductors like 14, 12, 10, AWG? Any special rules?
Yes, very specific rules in 240.4D. Regardless of their calculated ampacity from Table 310.16, there are maximum OCPD ratings allowed for these common small conductors, unless specific exceptions apply, like for motors.
What are those limits?
Generally, 14 AWG copper is limited to 15 amp protection. 12 AWG copper is limited to 20 amp protection. And 10 AWG copper is limited to 30 amp protection. Same limits apply to the equivalent aluminum sizes too, like 12 AWG-Al for 15A, 10 AWG-Al for 25A based on its ampacity. You can't put a 20 amp breaker on a 14 AWG wire circuit just because the wire is 90 degrees, the ampacity might be higher.
Okay, hard limits, 15A for 14K, 20A for 12K, 30A for 10K. Good to remember.
Absolutely.
Yeah.
And the code in Table 240.6 lists all the standard OCPD sizes, 15, 20, 25, 30, 40, 50, 60, 70 amps, all the way up to 6,000 amps. You generally have to select from these standard sizes.
Right. Now, some breakers are adjustable ATCBs.
Adjustable trip circuit breakers, yes.
Yeah.
These allow you to set the trip current within a certain range, maybe like a breaker labeled 600A to 800A. Section 240.6C permits their use, but the setting is often restricted based on the conductor ampacity. You can't just crank it up arbitrarily.
Okay, and most common breakers are inverse time.
Right. Inverse time circuit breakers. This means the time it takes to trip is inversely proportional to the amount of overcurrent. A small overload might take minutes to trip, giving temporary surges a chance to clear.
Like a motor starting.
Exactly. But a large overload or short-circuit current will cause it to trip almost instantaneously. It's that built-in delay for minor stuff, but fast reaction for major faults that makes them so versatile.
Makes sense. Let's quickly cover the fuse types again. Plug fuses.
Mostly older installations. Edison base are the standard screw-in type. S-type are rejection base, meaning you need an adapter, and once a specific size adapter like 15A is installed, you can't screw in a larger fuse, like a 20A or 30A. They come in ratings like 015A, 1620A, and 2130A.
Okay. And cartridge fuses.
Used for higher currents or specific applications. For rule types are cylindrical with metal end caps, typically up to 60 amps. Knife blade types have flat blades sticking out, used for ratings generally from 61 amps up to 600 amps, sometimes higher specific classes. Different classes, H, K, R, J, T, etc., have different interrupting ratings and time delay characteristics.
And circuit breakers, the resettable ones.
What automatic devices? Trip on overcurrent, you can reset them once the fault is cleared. Common residential breakers might have a 10,000 AIC rating.
AIC.
Amperes interrupting capacity. Which brings us to a crucial point.
Interrupting capacity, section 110.9.
Critically important. Every OCPD fuse or breaker must have an interrupting rating sufficient for the maximum fault current available at its line-side terminals.
Meaning it has to be able to safely extinguish the arc from a massive short circuit.
Exactly. If the available fault current, the potential short circuit current, is higher than the device's AIC rating, the device could literally explode when it tries to open the circuit under fault. It might fail to clear the fault, causing extensive damage, fire, serious hazards.
So you need to know the available fault current at that point in the system.
Ideally, yes. Or ensure the equipment installed has a suitable default rating for the location, like 10,000 AIC for residential panels, or maybe 22,000 or higher for commercial industrial settings where fault currents are often greater. Using a device with an inadequate AIC rating is a major code violation and a severe safety risk.
Okay, let's quickly revisit sizing OCPDs for continuous, non-continuous loads with those examples. 23 amp load.
Okay, 23 amps. Is it continuous? Let's assume it is for calculation. 23A by 1.25 equals 28.75A. You need an OCPD rated at least 28.75A. The next standard size up from 28.75A is 30A, so a 30A breaker.
Okay, 17 amp load, assume continuous.
17A by 1.25 equals 21.25A. Next standard size up is 25A.
Yeah.
Use a 40A breaker.
38.25 amp load, continuous.
38.25A by 1.25 equals 37.81A. Next standard size up is 50A. Use a 50A breaker. The conductor would also need to be sized based on that 125% calculation, e.g. needing an ampacity of at least 47.81A for the last example.
Perfect. That really clarifies the sizing process.
It's all about applying those rules consistently. Ampacity first. Consider continuous loads, then select the OCPD, always respecting terminal ratings and interrupting capacity.
So wrapping this deep dive up, mastering conductor ampacity and protective devices, it's not just for the exam, is it?
Not at all. This is fundamental professional competence. It's about ensuring safety, reliability, efficiency in every single thing you install. It's about preventing fires, protecting equipment, protecting people. It's the bedrock.
Okay, here's a final thought to leave our listeners with. How does that careful matching of conductor size and OCPD act like, say, the nervous system and the immune system of an electrical installation?
Interesting analogy.
And maybe what are some of those subtle real-world risks when they aren't perfectly aligned? Maybe things the code doesn't spell out in black and white, but that experienced electricians learn to watch for.
That's a great question. It makes you think beyond just the numbers. How does slight undersizing affect long-term insulation life? How does nuisance tripping impact processes? What about coordination between upstream and downstream breakers?
Yeah, lots to chew on there. I really encourage everyone listening to reflect on that. Revisit those application questions. Look for these principles on the job site tomorrow. You'll see this interplay everywhere.
Absolutely. The electrical field is all about continuous learning. Every challenge, every install builds on these core ideas. Keep digging, keep asking why, and you won't just be licensed, you'll be a truly skilled and safe electrician.